All right, good afternoon. So let's see. Today we're going to talk, excuse me. Thank you. Today we're going to talk about sequential logic. So we started that about a couple of lectures ago, and then I interrupted it to talk a little bit about multipliers. But we're going back to that. So this lecture we'll be mostly focusing on latches and flip-flops. And then I would like to talk about timing and more complex issues regarding how sequential circuits are operated in reality, how to distribute clocks and stuff like that, all those kind of things. But before we can go to clocks, I'm going to do another little detour and talk a little bit about wires, something we haven't really talked a lot about so far. And I think from the time we start thinking about clock distribution, we start thinking about power distribution, you're going to have to understand some of the properties of wires on a chip. We haven't talked about those at all. But before though, let's see what's up in terms of administrative stuff and so on. A couple of things. Number one, as you may be aware of, project phase number 2 is on. Be aware of that. It's due next Wednesday. It's not that many days from now. It's about a week. So we're moving forward. I hope that all of you, I got a number of emails regarding people signing up for different groups and so on and so forth. So I hope that all of you have signed up for a particular project. Remember, there's 3 phases. For those of you who have not, there's only one option left. You haven't signed up yet. You're stuck with, I think, option 2. Which means you get a 10% increase in delay, and you have to minimize power. That's the only option left. All the other ones are fully subscribed. Unfortunately, as I said last time around, the first ones are always the happy ones. Okay? Yes? No, I got those of you who emailed, they're basically all got what you requested. Okay? I forgot to mention that. So that's the project. If you have any questions, feel free. Yes? Is the template actually up? No, I'll basically bring the template up probably in the next couple of days or so. Probably by, definitely by Friday. Yeah. Absolutely. Let's see. If you have any questions regarding what you can do and what you cannot do, let us know. Ask the TAs, ask me, send me an email. Because there's one thing that, there's a couple of constraints that you should be absolutely aware of. I give you all the freedom in the world, but you cannot reduce the supply voltage, increase the supply voltage above 1.2 volt. That's one constraint. And the second thing is your circuit should do the same thing. After you've changed everything around, you're not allowed to change the input-output behavior. So which means that your impulse response should be looking pretty much the same as it did before. Okay? Because otherwise, if I start changing the functionality, it's easier to kind of, well, you know, eliminate a coefficient here and there. This kind of things help. Mike? Yeah, provided you did the right thing on the first phase of the project, right? That's right. Yeah, exactly. Obviously, Don't try to repeat the mistakes of the first phase. Right? That would be, if you had an impulse response that was wrong in the first phase. And actually, by the way, as I mentioned before, you will get the graded report back by Friday as well. So Friday, we'll get the midterm, get project phase 1, get what else is due? Well, no, the homework is due on Monday next week, so you have some more time for that. So it's a pretty hectic time. Okay. So that's the project. Any questions, other questions regarding projects? Things that are a little bit unclear? Also, you cannot really change the load factors. It's assumed that every output is loaded by a single register, and you cannot change the registers. You can only change the stuff that sits between the registers. Okay? Good. That's that. Let's see if there's anything else that pops in my mind. So, homework 7 due Monday. Graded. That's I mentioned that. Oh, we still have that hardware lab. I want to get that out of the way. So the planning is to have it next week. If nothing else comes in between, that's basically what we're planning for. Okay? Alrighty. And by the way, make sure that all your previous lab reports has been turned in and so on and so forth, because if you haven't turned in some of those reports, they're definitely late. But I'm going to start assembling the grades on that stuff pretty soon. Okay, good. We're done with arithmetic. And as I said, now we're going to go to latches and registers. And I didn't make a new handout this time. Well, I made one, but it's very much the same as what you had included in previous handouts. Previous handouts had already most of the register stuff in there, so making yet another copy didn't make that much sense. Okay, so let's repeat a little bit what we mentioned about sequential logic last time around. So sequential logic, the idea is now that you have a logic combinational block doing some Boolean logic functionality. So far, we've only discussed combinational logic, which means that the output is a direct function of the inputs at that point in time. However, that's not very useful because a circuit like that doesn't have memory. And try to figure out how much you can do without memory. The amount of options you have in terms of computations are quite limited. It's like a calculator without any memory capabilities. There's not much you can do with it. So a sequential circuit acts basically memory, and what memory does is take some outputs of your logic functions and stores it and then feeds them back into the network. So as a result of this, the output is now a function not only of the inputs at the same time, but also of the inputs of previous times, things past. So it remembers some of the history. And this could be finite or could be infinite. You can see that the history only lasts for a certain amount of time, but some history basically lasts for a very, 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 very long time, or even for an infinite amount of time. Okay? So the key question now that we're going to ask first is how to implement those memory elements. That's number one, registers, basically. And then we're going to think about how to coordinate all this interaction between logic and memory. That's what we call timing. Okay? But first we'll talk a little bit about memory. So what we want to do is create a block that basically takes a value and clocks it, or basically there's a signal that says store this. Generally it's going to be the clock for register. And then n times later, or a clock cycle later, you recoup that value and feed it back into the network. Okay? Now, this is also a review of what we have already discussed before. There's two types of elements that we use for in sequential type of networks. One of them is called a latch. The other one is called a register or a flip-flop. That's the other name that we very often use for it. A latch is an element which is really, it's kind of like a gate. When the enable signal, in this case the clock, is high, the input just passes to the output. So when the enable signal is high, this is just like a transparent gate. Input comes in and feeds right to the output. However, when the enable signal is low, in this phase, in that case, independent of the value of D, Q maintains its old value, the value it got after the clock basically went down. So when the clock is high, D just propagates to the output. you have a negative transition on the clock. At that point in time, I'm going to sample the value of D and bring it to the output Q. And then, independent of what's happening with D, Q remains the same. So it holds its old value, the value it had at the falling edge of the clock. So these are the different modes. Transparent, halt. Transparent, halt. That's the way we basically work with a latch. This is also called a level-sensitive device because when the clock is high, any change in D will basically reflect directly in Q. So we just pass the levels forward from the input to the output. Now obviously you can imagine that I also could have an inverse latch which operates at clock bar, which is going to be transparent when the clock is low and in halt mode when the clock is high. Yep, it's just an inversion that you have to add. Quite simple. Okay. Now a register is something which is called to be edge sensitive or edge triggered. In a register, the value is only going to be changing at the output. The value at the output, the value Q, is only changing at a given edge of the clock. So if you have what's called a positive edge triggered flip-flop, it means that on the rising edge of the clock, we're going to take the input value and store it at the output. So only at the rising edges of the clock do we basically change the values. This here, if you would have so you have D here, the clock goes high, you can see that Q changes on the rising edge of the clock. Okay. Same here, rising edge of the clock, Q goes low. This again, you could have a positive edge trigger flip-flop and a negative one. The negative one is on the falling edge of the clock signal. The positive one is on the rising edge of the clock. Okay. So that's kind of the basic definitions. Now there's some other parameters we need to have, mostly timing parameters. Clocks, registers and flip-flops and latches are a little bit more complex in the sense that the number of timing parameters we have is going to be a little bit more extensive. It's kind of summarized here. The delay of a flip-flop is not easy to define. What do you mean by delay? Well, it depends delay to what, right? If you have a gate with A, B, and C, we have a delay from A to output, from B to the output, and from C to the output. In a flip-flop, we have, or a register or latch, we have two inputs, D and the clock, one output. So again, we can see that we can define two different types of delay. The delay from the D signal to the Q, and the delay of the clock signal to the Q. Now, in a register, there's never going to be a direct delay going from D to Q, because whatever I do with D, nothing's going to happen with Q unless the clock changes. So the D to Q delay doesn't make any sense. It's never going to occur, unless obviously you mess up your design. But in general, there's no path, direct path from D to Q. The only way to change Q is to apply a clock edge. Most of the time, as I said, positive edge trigger flip-flop, rising edge, negative, falling edge. So the only delay we're going to talk about here is the C to Q delay, the clock to Q type of signal delay. Now in the latch, the world is a little bit different. Because in a latch, if I'm in transparent mode, the input arrives and propagates very nicely to the output through a number of gates. So this is what's called a D to Q delay. But obviously, when I apply, let's say, for a positive latch, if I apply a rising edge of the clock, before that, nothing has happened. The gate, the latch is in hold mode. I apply the rising edge of the clock, I go to transparent. At that point in time, my output is going to start changing based on what the D value was. That's what we call, again, the C to Q delay. Rising edge of the clock, what time does it take for my output to change? Okay? This is a very important parameter. Because remember now, when you did logic, like you do in the project, in the design you typically will have a set of latches or flip-flops, and then logic, and then another flip-flop. So you can see that when I apply a clock edge here, it's going to take some time before this is going to start changing, and then propagate to the logic. So this delay here is going to be an integral part of your delay of your network. The first part, if you look at critical path of any path in your network, is going to start with a C to Q delay, followed by logic delays. Okay. So then you might ask, what does this thing do here? Is that adding delay to it? Well, it acts as a load, obviously, to the network, like you do in the project. But there's some other constraints that follow as a result of this as well. And this is kind of shown in this slide. We have some other clocking parameters that are very important. If design goes bad, very often it goes bad because of violations against some of the things I'm going to talk about right now. It's what's called the setup and hold times. Setup time of a register or latch basically is the following thing. Suppose I'm going to take, let's say, a latch. I'm going to turn off the clock. Right? I'm going to make the latch in hold mode. Now the question you might ask yourself is, can I still change the signal just at the time I change the clock? Right? If I change the signal just at the time I drop the clock, the question is unclear what value you will see stored in the latch. Is it the one that basically was just before, or is it the one that was just after the transition? So typically a register will require that your data is stable a little bit before I can basically drop the clock. So okay, keep your data stable. It has to be stable till a certain amount of time, otherwise it's going to fail. Or just a certain time before that. Right? So this is called the setup time. So we have to keep our data stable a certain time t set up before we can change the clock edge. Okay? Very important. Similarly, if I change the clock and I just say, okay, I'm going to store the data, now I could remove the data instantaneously after that. Right? It says, here's the clock goes down, now I'm going to remove the data. Question is, how fast can you remove the data? So the data is stable, in the setup time, you have it there. I basically load the clock, or rise the clock, depending upon the registry you have. And now I can say, no, can I remove the data right away? Or should I leave it sitting there for a while? And the answer is yes, you have to leave it sitting there for a while. It's called, obviously, the hold time. How long do you have to keep the data stable after the triggering clock signal has disappeared, or basically has finished? So that's the hold time. These are very important constraints. Meeting those setup and hold times is absolutely essential. Because if you don't, you might store some bogus into your memory. And computation bogus typically doesn't generate a lot of good results. So very important. Okay? Now we'll give you some more way. I'm going to discuss in about 15 minutes or so how actually to compute the setup and hold time. But before doing so, let's talk a little bit about the type of latches, and then you will see why we have setup and hold time constraints on the latch. Okay, so that's the timing definitions. Now let's look at the way we can store data in a CMOS process. Okay, there's many ways of storing data. I could put it in a superconducting coil and have the current flowing around forever. It's one option, which people have definitely considered. I can, there's a whole bunch of things. I can store some charge on the capacitor. Charge is there, I disconnect the capacitor, and if it doesn't leak, the charge is going to stay there forever. So if there's no charge, that's a 0. If there's charge, that's a 1. That's what we call a dynamic memory, for a good reason. Right? Because you can imagine that a circuit without leakage is very hard to find. They always leak. The switches that connect your capacitor are going to have subthreshold currents. There's going to be diodes connected to it. It's going to leak away. So if I use dynamic storage, you know that the data is only going to be valid for a certain amount of time, and then it's going to disappear. So one way to do that is rewrite the data very often. That's called refreshing. Or you assume that the data only needs to be there for a certain amount of time. For instance, if I have a register that sits in the middle of a data path, every clock cycle I'm going to overwrite the data. So it doesn't matter. As long as the data lasts for a clock cycle, I'm okay. However, if I have a main memory of a computer, I put some stuff in there, my program, my data or something like that, I assume it's going to be there for a while. So if I use dynamic approaches, I'm going to have to refresh it regularly. Every charge that's lost, I'm going to replenish a bit. Okay? So that's one way of storing it. That's very simple, right? The only thing I need is a capacitor. It's the simplest way I can think about basically building a piece of memory is a capacitor with some switches to it. Okay? That's called DRAM, by the way. And DRAM is the cheapest way of storing data. But more about this later. However, there's another way. So this is a dynamic approach. You have a capacitor, you have a switch, you charge a capacitor, and when you need the value, you just read it out using a inverter. The inverter obviously does not impact the charge that's stored on this capacitor. Actually, very often the capacitor is the capacitor of the input of this particular gate. Right, every gate has an input capacitance. I can just use that capacitor to store my data. Okay. Now, there's, however, another approach, which we call static. Again, static doesn't basically rely on specific storage mechanisms like a capacitor does. In the static type of memory, I'm going to rely on logic to ensure that my value remains stored. And the only way to really do that is by adding feedback. Okay? If I have a circuit with feedback, you will see from the time you have feedback, you create memory into this element, at least if you do it right. You either create an oscillator or you create something. It's dependent upon the type of feedback you're giving, positive feedback versus negative feedback. So let me show you a very simple example. Here's the most simple way of storing something. I take two inverters, and I connect them together with the output of the second inverter. I connect to the input of the first. A loop with two inverters. Obviously, this has to be an even number of inverters. When I have an odd number of inverters, I'm going to have an oscillator. Okay, so you have a different type of feedback. But here we have positive. We have basically negative feedback, and what this creates is basically a stable network. So if you look now at what this thing can do, the best way is actually to draw the voltage transfer characteristic. So if I take inverter 1, it's inverter 1, and I draw the VTC, we know that VO1 is a function of VI1. Okay? Fairly straightforward. Here's your voltage transfer characteristic. Now, VO1 now becomes the input to the second inverter. So what I'm going to do is rotate the voltage transfer characteristic of the second inverter. So VO1 is VI2. So this is the input. This is the output of the second inverter. And the voltage transfer characteristic is like this. I just kind of rotate it around. But now what I do is I take VO2 and I connect this back to VI1. So I collapse those two on top of each other, really. And what you get is the following thing. So this is your voltage transfer characteristic. So this is your first inverter. And this is your second inverter. And since they're all connected together, the only stable points that I can operate this thing at are basically where those two cross. These are the only real solutions to this network. Turned out there's three solutions. A, B, and C. Now, A is easy to understand. Suppose that VO1 is equal to 0. This is 0. This is a 1. Then this is 1, and we have a stable network. Right? You're in two inverters connected nicely to each other. 1, 0, 1. Bingo, we're done. Another option would be have 0 here. That's 1, and that's 0. That's another solution. Okay? Now, the interesting part of this network is that as long as I keep it like that, these values are going to stay there. This is going to stay as 1, or this is going to stay as 0. Nothing is going to happen. So it is a memory. It's a, but it's, what you would like to have actually for a real memory is something which is called bistable. Bistable, bi means two, right? Bistable means you have two stable states. One is a 1, the other one is a 0. Now, as I mentioned, if I look at this voltage transfer characteristic here, you see there's a third point. The watts that sits in the middle. That's really the solution when I apply Vm here, I get Vm here, and I get Vm here. I bias every inverter in its switching point. I apply the switching point at the input, and I get it at the output. That's the definition of the switching point. So this clearly should be a legit solution as well, and obviously it's not very useful, because now I can have a memory that sits in this indeterminate state. It's not a 1, it's not a 0, it sits in the middle. Fortunately, this state is not a real one. This is what we call a meta-stable state. Meta means half in Greek. So it's kind of half stable. What it really is, it looks like a stable position, but it's not. Because anything that happens with, suppose I bias very carefully. I'm sitting there and I'm going to very carefully apply VM at the input and I force everything to be at VM. So from time I get this thing loose, some thermal noise, some electron flying by will basically create a disruption from that VM point. Any noise actually will move thing out of VM, and what you'll see is that rather than going back, if the noise is taken away, rather than going back to the metastable point, my flip-flop here, or my latch, is going to migrate to either the 1 state or the 0 state. So this metastable state is not a real stable position. Anything that happens will force it out and move it either to the 1 state or the 0 state. So this really is a bistable element. Now, let me show you why it is that any change in state will basically cause our inverters to kind of drift away to one of the stable states. Suppose we're in the middle, and actually this is kind of an interesting exercise. Try to do this in SPICE. Try to put 2 inverters in a row, in a loop, and make them stay in a transient simulation. You put a transient simulation, you force them in the beginning at the VM points. And then you say, okay, now I'm going to have a transient simulation and see what's happening. It's extremely hard to keep it in that VM point. It will always run away. A purely quantization noise of the SPICE simulator already might cause it to basically move to one place or the other place. It might be very slow. If I'm very nicely smack on VM, it's going to take a while to move out there, but eventually it will. And the reason for that is kind of explained here. Suppose I'm in a metastable state, and now what I'm going to do is say I'm going to take VI1. These 5s are equal to equal signs. This is a interesting font artifact. So I move this thing just a little bit out of the metastable point. So I'm changing VI1 just by value D. A little bit of noise. So what's going to happen with VO1? Well, I basically have my voltage transfer characteristic. I need VI1. And VO1 is going to be somewhere like this. Now I apply this to the next inverter, the second one. You can see I apply this input, I get this output. So I go basically from this position to this. And then I apply this again to the next chain, and I go to here. And so on and so forth, and you end up here. So very rapidly we see that we migrate away from this and move away to one of this particular point by just applying this from voltage transfer characteristic 1 to the second one, the first one to the second one. Okay? So a couple of iterations here are done. Now, why is this happening? Well, it's very simple. It is because of the fact that in this loop we have a gain larger than 1. Any change from that middle point is going to get amplified by the combined gain of the 2 inverters. So remember, a gain of an inverter is about what? 10, 15, 20? CMOS inverter, that's the gain you have in the middle region. So the whole loop has a gain of 10 by 10 or 20 by 20, a couple of hundred. So that's really going to change. A small signal that I apply that deviates from the midpoint is going to multiply by a factor 100 quickly. And you're going to move it out to the sides, being you're done. So try it when you would have something like this. Suppose I create a very bizarre gate that has this voltage transfer characteristic. And then the other one flipped around obviously has the other one. You will see that here you get just the opposite. Instead of moving to the side, you're just going to move very rapidly to the metastable point. So that would not be a good bistable element. It's actually something that creates metastability. Okay? So that's cool. So the simplest memory element I have is 2 inverters in a row. I put it in a certain state, the 1 state or the 0 state, and it stays there. As long as I keep the supply voltage on. Obviously, from the time I remove the supply voltage, I'm toast. Then you need another type of memory. We're going to talk briefly about that. Things like non-volatile memories. Flash memories, for instance, are memories that retain their value even if I turn off the supply voltage. Some interesting tricks and ways of doing this, but we're not going to talk about this right now. We'll talk about that later. Okay, so that's cool. So this is my latch. Oops. But this is a pretty useless device. Not much I can do with this, because now I have to find a way to write a value into it. I have to be able to change it. So there's 2 ways of changing the value of a bistable. 2 ways people do this. The first one is what I would call the macho approach, and the second one is a more subtle approach. The macho approach is I'm going to basically show a lot of muscle. I'm a 1. I'm going to come in there and going to force the thing to go to 1. So here you have your latch. What I can just do, apply on one of the inputs, apply a switch, let's say, a pass transistor. I apply a 1 here, and with this switch, I force this node to become a 1. So, okay, I'm going to make you become a 1. But obviously, I'm fighting here. There's a battle going on, because this inverter, if this was a 0, this is a 1, this inverter would really like to keep a 0 here, because this value is still 1. So you fight against that inverter. So the inverter tries to keep this at 0. The pass transistor tries to force this to a 1. So a battle. Now, when you think about battles, we think about ratioed logic. Right? Ratioed logic is the same thing. You try to overpower it, and you try to move things to a new state. So you have to be careful here, because now you have two forces against each other, and if one of the forces is not strong enough, you might not be able to flip the thing around. So very often what we're going to do, for instance, like in this case, we're going to make the feedback inverter a little bit of a weak one. It doesn't have to be that strong. The pass transistor we have to make strong. And in that case, you can see that when the battle goes on, we can make the thing flip around and go to one state or the other state. Okay? So this is what we call forcing the state. You just take the latch, and we're going to move physically the node to a 1 or a 0 position. And then once you remove that force, it's going to stay in the new position. Right? Now, here's another approach to do that, which is a little more subtle. So, one way to force things to a certain state is, what we have here is positive feedback. We have this feedback loop, right? That basically is going on. What we could do is remove the feedback for a while. When you want to change the value, I'm going to break the loop. And now you have, instead of 2 inverters in a loop, you have basically 2 inverters in a chain. I apply a new input to one of those, and the whole chain will basically go to the right value. And then I remove the thing, basically connect it back, and we're done. So this is kind of the way we can do this. So when the clock is high, in this case, this is a latch. When the clock is high, you see that this pass transistor or this transmission gate is on. This one is off. Okay? So if I apply a 1 here, I get a 0 here, I get a 0 here, I get a 1 here, I get a 0 here. Okay? I put my register in a certain state. There's no feedback, there's no battles going on, everything is nice and easy. And then we turn off the clock, we turn off this switch, turn back this switch on, and we maintain the value in the positive feedback loop. Okay? So what this is nothing else than a multiplexer. If you look at it, the circuit that we see here, and let me clean it up a little bit. This circuit is a traditional multiplexer. I have 2 switches, one working on the clock, one or the other one on clock bar, and inverter behind that. That's a typical pass transistor-based multiplexer. And we choose either the old value or we choose the new value to go in there. So there's 2 options, old value, new value. And that's the way you basically regulate this particular switch. This is a little bit easier because I don't need that overpowering effect. You're never going to run into ratio problems like you might run here. But this is somewhat simpler. Just basically this inversion, these 2 inverters in a row is a fairly simple type of latch structure. So this latch we very often call the pseudostatic latch. It's one way of looking at it. It's kind of, it's like a dynamic latch, but we basically we have a way of conserving the data behind it. Mux-based latches, same thing. This is kind of a other way of writing down my latch. You take Q when the clock is equal to 1, like this is a negative latch, it's transparent when the clock is equal to 0. When the clock is equal to 1, we just close this loop. When the clock is equal to 0, we feed this signal in. And you have obviously the opposite one. When the clock is high, the clock, in this case, it's transparent. The input goes to the output. So that's a very simple way of looking at latches. Now, latches are a nice element, but you have to be darn careful with them. They're the simplest memory elements, right? You have one input, D input, Q output, is single state, quite nice. However, suppose now I want to implement a piece of logic or sequential block. What I could do, let's say, is take my logic here, and I say, well, logic and latch have the same kind of notation here. So let's call this logical, and this is the latch. And I apply a clock here. Okay? So I have a chunk of logic. Could be an adder, multiply, whatever it is. And I take the outputs and I feed them to latches, and I go back to the inputs. Can you see a potential danger here? Any way this thing can go wrong? Think what happens if my clock, this latch is transparent when the clock is high. Okay, think a little bit when what's happening when I keep the clock high for a long time. The latch is transparent, right? What does that mean is the input propagates to the output. What could happen here? Suppose I keep it on for a very long time. So you have an input here, you have a certain value Q or D, and I keep this on, and what's going to happen? Suppose I never turn off the latch. I keep it on. I keep it in transparent mode all the time. Do you know what the value is going to be at the output? Can you predict what it's going to be? Remember, the reason I'm adding a latch or a register is to create some memory of the past. At least a deterministic memory of the past. Think what's happening when you have a gate here, you have a circuit in a loop, your logic computes, and then the gate is always open. It's always transparent. What's going to happen? Your data is going to start racing around. So my input goes here. Okay, so no problem. I can go here. It goes back to the input. You start doing the computing again. You get a new output. It goes back to the latch, and it keeps on racing around. It's chasing its own tail, going around and around and around. And then suddenly I lower the clock. Do you know what you're going to get? No. Fat chance, right? It really depends upon exactly what the delay is going to be and so on and so forth. So this rate, you typically would like to have the data to go one compute cycle, but in the latch, clock comes in, next compute cycle, next cycle. But here it goes around and around and around and around. So that's the problem with latches, is that the feedback loop, when the latch is in transparent mode, you basically connect the inputs of the circuit just to the outputs. It's a purely asynchronous circuit, as we call it. And predicting what's going to happen here is going to be very hard. So, how can we get around that? How would you basically get around this particular fundamental problem of pure latch-based design? There's a simple solution, but it's hard to implement. And there is a little bit more complex, but easier to implement.
Maybe we should look at the clock edges instead of the high and low.
Yeah, but that's cheating, right? You start using registers. So, fine. Flip-flops, edge-triggered flip-flops, absolutely. That's another way, but we'll come back there. So let's stick to latches for the time being. So what's the simplest way? How can I prevent the thing from racing around? What is the necessity for this thing to chase its own tail? What's the requirement from a timing perspective? If I think about what happens if I play around with the clock cycle, the time that the clock is high. Can I get a race if I reduce so you have a clock here, it's high, this is transparent, this is halt, right? Halt mode, you're fine. The problem really is when it's in high mode, that your circuit basically can go around and around and around and around. So what can I do to prevent multiple cycles around logic? No clue? Look at the clock edge. Or the clock, this clock cycle here. So I have this. Right? What is necessary? What's the requirement for this on time of this latch for a race to happen? A race, as it says, it's basically it's a circuit or a signal that chases its own tail. That is correct. So not the edge, but basically the on time of the clock has to be longer than the delay of the loop. So if I make this thing shorter than the delay of my logic, I'm going to be fine. Right? I won't have a race at all. It doesn't have the time to go around and bingo, I turn my. So if I make this thing like something like this, narrow pulses, that's going to be fine. Right? I'm going to be, as long as this edge, or basically the on time, the duty cycle of this clock is smaller than the delay of my logic. So that's a game we can play, and I'll show you in a minute, well, not in a minute, let's say 15 minutes, a set of latches, a modification of latches that will exactly do this. It will make sure that the pulse that the latch is seeing, or that the time that the latch is going to be in transport mode is always very short. Just a little bingo, turn it on, turn it back off. And you're going to be safe. Because playing around, this is playing with fire, right? I say, okay, I can play around with the duty cycle of my clock a little bit. Now you know that a single piece of logic doesn't have a single delay. If I have a complex block like a multiplier, there's multiple paths. They could be short paths, it could be long paths. So no, not every delay is the same. So which one do you pick? The shortest path of the whole thing? So you say, well, my pulse has to be shorter than the shortest path in the delay. But it's also depending upon the data I'm applying. It might be also a function of process variations. You not always think. Noise might come in, change the delay a little bit. It's very tricky. As I said, it's playing with fire. And the only way to really do this is make sure that it's very, very short. Otherwise, I wouldn't even dare to do it. Well, no, I'm retracting that. If I'm really in a good day and I like to do a lot of simulations and really pushing to the edge, I might do it. But rarely, very rarely. It's only when I have plenty of time at hand. And I'm pretty sure that I can make it work. So that's option number one. So it's a simple one. You apply a simple pulse, small pulse, and bingo, we're done. So it's simple, but it's still a little bit scary. So what's the other option? Suppose now I do a small modification. Let's do that. Let's say I'm going to divide my logic into two parts. Logic 1, L, logic 2, latch, and connect it to each other. And this thing I'm going to clock on phi, and this I clock on phi bar. Okay, so instead of having one latch, I put two latches in there. Divide my logic, and I put two latches in there. But I clock it on opposing cycles. Now you see there's never a possibility, because when this thing is in transport mode, this is in halt mode. When this is in halt mode, the other one is in transport mode. There's never going to be a complete path around the loop. It's always going to be broken somewhere, and you're always going to be safe. Okay? So one way of doing latch-based design is actually having two clock phases and distribute them to the logic. Again, this is something that people do, but rarely. I see it in very high-performance designs. It's often done, and actually has some interesting benefits. You can actually cheat with this approach. It's actually making something faster than it should be. It's called slack borrowing. You borrow time from another clock cycle and things like that. So you can do fun stuff with it. This is not 141 material. I wouldn't go there. It's 241 actually. People play around with this type of things. Latch-based design. But in general, it's something that is avoided. So we have done that, mux-based design. Why do I show this back again? I'll come back to that. So this is what latch-based design look like. You have logic, you have an N latch or a P latch. You have two different type of latches working on different clocks. You call an N latch when it is transparent when the clock is 0. P latch is transparent when the clock is equal to 1. So that's what I just showed you. Now there's another thing that you should be aware of. If I use latches using this kind of pseudo-stat or basically multiplex-based approach, remember we have now two clocks here, a clock and a clock bar, and a strong transmission gates. Now, as we know, transmission gates are kind of nice, but we try to avoid them. The problem with transmission gates is that you have to have a PMOS and an NMOS, they act extra load. So I rarely see anybody implementing a latch this way. It's too much overhead. It's too slow. So we're going to rather do something like this, where we use pass transistors instead. Okay? So I have a first pass transistor, which is your halt mode, and then the other one is the latch mode or the transparent mode. Okay. So as I mentioned, for this thing to work, I always need two clocks, a clock and a clock bar. You need clock and clock invert. Okay. Now that's kind of a pain, because there's a couple of things that we have to worry about. Number one is I have to distribute two clocks through the chip. Now one clock is already bad. Right? You have one clock that's, remember what I told you about the clock? It's the worst signal on the chip, because it goes everywhere, it connects to everything, it has the largest capacitive load, and it changes every clock cycle. So it's the highest power consuming type of component on the chip. Now I make two of them. Right? So I double the power dissipation of my clock system, approximately. Not really, because the fan out, but you make things a little bit worrisome. There's another danger with this thing. It's very nice on a schematic, right? I go into to Spectre or something like that, or in a high-level simulator, and I draw my clock like this. Perfect edges, and clock bar are perfect inversions of each other. Now try to make two signals that are perfect inversions of each other. It's not easy. Right? If I make an inverted value of the clock, I put an inverter in between. And already the second clock is going to be delayed version of the first one, inverted. So you will see the first clock, and the second one might be something like this. Right? So they're not perfect inverted signals. So why can this be a problem? Well, if you look now very carefully, there's a certain time here that both my clocks, both clock and clock bar, are going to be 1 at the same time. And there's going to be a period that both of them are going to be 0 at the same time. Now think about what's going to happen when both clocks are on at the same time. This is on and this is on. Okay? What you have is now, again, a battle going on. We're fighting against each other. You have one signal coming in and the other one is still trying to force the old value. It's going to take some power dissipation and potentially might create some wrong values, because this is a non-ratioed logic, and suddenly we create some ratio type of constraints on it. Okay? So that's an issue. Clock overlap, and when both of them are 0, this becomes a dynamic memory. Right? All the switches are open. We just have two inverters kind of happily hanging out there. But basically, this is a dynamic node at that point in time. It's floating. So charge loss and things like that could happen. Okay? So the idea of non-overlapping clocks is somewhat of a untruth. Right? It's impossible to make clocks which are perfectly symmetrical or symmetrical inversions of each other. And if they're not completely, we can have some problems with our latches. The situation is actually worse. Suppose we're going to talk about this in a couple of lectures, but suppose I take a big chip, right? Centimeter on the side, fairly decent size of die, lots of processing elements. So now I'm going to basically start wiring my clock. So this is a zigzag signal or a tree signal. There's a whole bunch of ways, but I wire my clock to this thing. Well, let me choose a different color here. Let me take a green clock. So let's say I distribute my clock like this, and then this goes like that. You might ask why I draw it this way, but believe me, this is a good way of doing it. So this is my first clock. Now I'm going to bring my second clock in there. The chance that this is going to be exactly the same is almost impossible. Right? They would have to sit on top of each other. So this is going to be a different network, which is going to be, I might route it completely different, but that would be a really bad idea. I might try to mimic the two each other, but that's a real bad idea too, because if you put them close to each other, they're going to couple capacitively into each other. You're going to see all kind of free-through effects and all this kind of things. So the bottom line is that your clock distribution network for both clock and clock bar are going to be different, which means that the delay along those networks is going to be different. It's going to once again shift those clocks with respect to each other. Again, this idea of a purely symmetrical clock, even if I could generate purely symmetrical clocks at the income, is going to shift with respect to each other because of different delay factors. And again, it's going to be non-overlapping. So you have to be aware when you use mux-based design that overlap of clocks can cause problems. Yes?
Can you just use on each mux itself have a little inverter and have the clock go into that inverter because the clock's not?
Very good. Yes, that's definitely what people sometimes do. It makes your register a little bit more complex, because now every register has to have an extra inverter. But the delay is going to be very nicely controlled. Right? It's only going to be that little inverter that sits in the register that helps me to create that inverted signal. So we know exactly how much non-overlap you will basically be getting. Absolutely. I've seen this quite often done, and it basically saves one clock distribution network. Okay? So it is something that people definitely have considered and are doing. Okay? And we've seen that. Now, so be aware of that, right? Clock overlap, and I'll come back later to it, to some other ways of getting around it. How I actually can eliminate some of those problems. Now, remember my latch-based logic? I put the latch, and I have two latches, and I have logic blocks. Right? And this is phi, and this is phi bar. Now what I could do is say, well, rather than dividing up my logic, what I can do is move this latch and just put the two next to each other. I have a first latch which operates at phi, the other one on phi bar, just in one entity. So something like this. Right? I have a first register-based, a multiplexer-based register, and I follow it by a second one. If my clocks are perfectly non-overlapping, so one of them are going to operate on clock bar, so this is a negative latch, it's transparent when the clock is low. This is a positive latch, it's transparent when the clock is high. Okay? So you can see that if the clock doesn't overlap, right, that's an assumption. Assume that we have perfect clocks. You can see that there's never going to be a path from D to Q. It's impossible. Right? Either this latch is going to be in transparent mode and halt mode, or this latch is going to be in halt mode. They're never going to be in transparent mode at the same time. So this circuit always breaks the loop. Okay? Actually, if you look very carefully at this, see what's going to happen. Suppose, again, as I mentioned, this first latch, which you call the master latch, is going to be transparent when the clock is low. So when the clock is low, right here, the clock goes low, we see that our D value, the input value, which is changing, is propagating to QM. This is in transparent mode, so anything that happens on D happens on QM. However, Q, the output here, since this latch is in halt mode, Q just remains in the old value. Nothing happens there. So this is transparent, this is halt. Okay? Then, when the clock goes high, on the rising edge of the clock, we flip them around. The first one goes now into halt mode, while the second one is going to go into transparent mode. So we're going to sample at the falling edge of the clock, on the rising edge of the clock. We take the value of D that was applied at a point in time and store it at QM. QM now becomes constant. And since the second latch is in transparent mode, it's just the output of it is going to just propagate to the output. But since this is a stable value, this is going to be stable as well. Okay? So by putting these two latches together, I've done two things. A, I made sure that I'm never going to have a race through the network. And the second thing, I have turned this from level sensitive into something which is edge sensitive. Because this latch is only going to change at the output on the rising edge of the clock signal. That's the only time a change can happen. You take what's happened, the first latch sits there, basically follows what's happening at the input. Clock rises, we shut that one off, we store that value, and we propagate it to the output. Okay? So this is why we call this now an edge-triggered register or flip-flop. Edge-triggered because it reacts on the rising edge, or if I would do the inverse, on the falling edge of the clock. It's also called the master-slave flip-flop. You have a master flip-flop that tracks the input, and the slave is just there to drive to the output. And they work on opposite phases. Okay? Very commonly used technique. It was a very solid way of implementing a register which is very solid and very reliable from a timing perspective. Okay, so here's one example with multiplexer based, but boy, I can come up with many, many different versions of this. What this really does is, like here's an example obviously of what you mentioned before. The delay here is implemented as an inverter into the master slave flip-flop. So we know that the delay between those two and the overlap is very much confined and is determined by basically the delay of this inverter. Okay, so this is how it operates. So you can see D changing. D changes, nothing happens with the output. Q remains value until the clock goes high. Clock goes high, bingo, my output changes, and D propagates to Q, and the output value changes around here. And the most important delay here is the delay between the clock edge and the time that Q changes. That's my C to Q delay, clock to Q. Clock changes, a little bit later the output of my register is going to change to Q, to 1 or 0. And like obviously, again, there might be different delays for the low to high and the high to low. We know that. We expect that. Okay. Now, we've shown you these master-slave type structures. We've shown you latch type structures. Let me come back now a little bit to this discussion of the setup and hold time things. Trying to understand why is it such that we have to be concerned about this. Why are setup and hold times important, and how do you measure them? Well, here's an example. This is an example of a latch. Actually, no, this is a flip-flop, actually. Same thing as we just showed before. It's this multiplexer-based master-slave flip-flop, where you would expect, again, there's some font issue here. This is equals, that's a dash that you have to basically put between those two here. So you see that you have your D, and then you apply the clock edge, and we hopefully will see some changes, or no changes. Turns out when it's D set up is equal to 21 nanoseconds. So we can keep 29 nanoseconds between those two. Okay? Sorry, 210 picoseconds, 0.21. So 210 picoseconds. Simulation. And we'll see in that case that this intermediate node makes a very nice transition. The intermediate node is the one you can see here. That's I think it's another. That's the node which sits between the two registers right here. That's IT-T2. That's this particular intermediate node. QM is this output node. What you see is that QM makes I2T2 basically makes a very nice transition, and obviously QM basically follows. We get a very beautiful value. Everything is perfect. However, what I'm now going to do is move D a little bit. I'm going to change. I move D so that it's getting a little bit closer to the clock edge. So I'm going to still make a change of D less than 210 picoseconds before the clock edge. Actually, I'm going to move it to 200 picoseconds. Not much. 10 picosecond change in the distance between those two edges. What you see is that you would hope that, you remember this is a feedback loop. You open the feedback loop, you put a signal, and then you close the feedback loop and you say, okay, now you stay stable. That's the way these pseudostatic latches work. Now, if you basically have not enough signal, and then you say, okay, I'm going to close the loop, you might have thought it was already going to go to the other state, but you don't have enough value. The swing is not far enough yet. And what you see is that the thing changes its mind and it goes back to the old value. And bottom line is Q basically drops to 0 and the result is wrong. So just moving those edges a little bit closer makes something that works very nicely. Here you see I'm far enough along that I2T2 node goes all the way to 0. Here it changes its mind and goes back to the old value. And bingo, things are wrong. So this is an example of why setup times are important. If I really try to cut it too much close to the edge, I'm going to be in trouble. Now, the question is, what is too close to the edge? How do you measure that? Well, I can start simulating and I can start moving the D value closer and closer and closer till suddenly the circuit fails. That's one option. So I just take the D value, I have my clock edge, and I keep on moving them closer to each other and observe what's happening with the outputs. Right? That's one option, but what you actually will observe is that moving things closer to each other will have some secondary effects. They're not independent. And let me kind of illustrate this with this case here. Turns out that suppose I have a setup time here. Okay, I have my clock edge fixed. Here's my D edge, and I'm going to try to move it closer and closer. Okay, what will happen with the Q value? When I'm far away, right? When the D edge changes very far away from the clock, everything is beautiful. You will get a very nice transition on Q. Then when it really gets very close, you will get this failure event. The circuit will basically go up and then start to go down again. So that's clearly a failure. This is success. This is a good circuit. But what's happening in between? Turns out that if I keep moving D closer to the edge here, what you see is that the C to Q delay that we see here is actually increasing. The ramp at the output of this thing, initially it's a beautiful, nice output ramp, and then slowly but surely you see a degradation in the output slope, till suddenly it fails. Right? So you see a transition happening. Now, is it okay for us to wait till it's failing? Or actually, it's almost just as bad to see that if I move something too close to each other, I'm saving at the setup time, but I'm making my CTQ delay worse. Right? Yeah, one has an impact on the other one. And then finally, your CTQ becomes infinite. That's obviously bad. It fails. But you see a gradual degradation here of the CTQ delay as a function of setup time. So the way to draw this is say, well, gee, I could have a graph where I plot the C2Q delay. Right? The C2Q delay, if you put your D way up front, right? I say, okay, let's compute the value of the C2Q delay. I apply my edge. What's my delay at the outputs? Okay, that's my steady state value. Now I'm starting to reduce the setup time. Okay, I'm reducing the setup time. Initially, nothing will happen. I'll get closer to the edge, but you're still far enough away, so the value of CTQ remains constant. But then I get closer and closer and closer and closer. And what you see is that, as I showed you here, you see a degradation in the C2Q delay. The C2Q delay starts to increase. And the closer you're getting, the more it is increasing. It goes up and up and up, and suddenly it fails. Your circuit doesn't work anymore. So how would I now define CTQ? Or the setup time? Is the setup time the time here where it fails? Or is it the time where it starts to change? Or something in between? It doesn't really matter. You have to come up with a definition. And the definition we're generally going to use is the setup time where we see the 5% degradation in the C2Q delay. So if you have your C2Q delay without any setup constraint, you add 5% to it, and when it is 5%, your C2Q goes up at 5%. That's going to be the definition of my setup time. Like in this case, 5%, bingo. That's the setup time. Anything that's closer than that will impact my CTQ delay too much. Okay? So that's the way I define it. Now we can do the same thing with the hold time. We start with the hold time, which is way later. Right? We basically keep your signal, clock edge happens, and then I keep my input signal valid for a long time. And then I keep moving it closer and closer and closer and closer and closer to my clock edge. And what you see is your CTQ delay will start to go up again and potentially fail. Again, where we see deterioration of 5% in C2Q, that's what we call the hold time. Okay? And this can be easily generated by computer. Right? You just do transient analysis and you move the things closer and closer and closer. And you basically look at what's happening with your delay. You look at the 5% point and you're basically there. Now this 5% point is totally arbitrary. Just some people, I could have just as chosen 10%. But 5% seems to be something that people feel comfortable with. Okay, that's not a really big degradation yet in overall timing. So let me just explain this with a simple example. Okay, so you have a transmission gate, basically a transmission gate based latch. Okay, so we have our clock here. It's a transmission gate. So this latch will go off, of this pass transistor here will go off when the clock goes low. Right? So when the clock is high, this transmission gate is in transparent mode. And when we basically drop the edge, then we basically turn off the switch and we're going to keep on the old value. We go in hold mode basically. Right? Clock high, transparent. Clock low, we're in hold position. So let's see what's happening with a day delay. So we have a clock edge here. We have our clock edge. And we change the data way before the clock edge. So, and then we keep it stable. Okay, that's the ideal situation. You have plenty of time, your data is there, everything is beautiful, everything is stable. And now what we're going to do is start moving this data edge closer and closer to the clock edge. So we move this up and up and up in this direction and see what's happening. Now, let's think about what physically is going to happen if I move too close. Right? So if I change the input at D here, let's say I go from 0 to 1, what's going to happen is that D1 is going to go from high to low. Okay? And then there's a capacitor sitting here. And we're going to charge this capacitor to this pass transistor or transmission gate. Now suppose now that I turn off the clock in the middle. So you try to discharge or charge this capacitor. In this case it's discharging. Discharge the capacitor. Suppose I open the switch while the discharging hasn't happened completely yet. What's going to happen is I will have some remaining value sitting there, or I will not be completely at VDD. So the signal that's stored on this capacitor here is now going to be 0 VDD. Okay? And that explains why this inverter here is then going to get slower. I don't get the complete swing, I have less drive, and you see your C2Q delay starting to basically increase because I don't have enough drive signal available to me. Okay? So let's do this kind of in an animated format. Let me just clear out things. So let's just move forward here. So this is the ideal situation. This is what my C2Q delay is. Okay, this is my first setup time. Setup time, I basically change things way before the clock edge. Now I'm going to move it. I move it up a little bit. Second one, still plenty of time, nothing happens. I still charge up or discharge the next capacitor perfectly. Another step, I get a little bit closer, and what you start seeing here now is that instead of going all the way down to 0, my remainder value might be a little bit off 0. I don't really get a perfect ground signal anymore. And as a result of that, you can see the delay, the C2Q delay, is starting to inch up a little bit. I just don't have as much drive anymore. And you can keep on doing that, and bingo, finally the thing fails. And again, the definition is we measure this value, we add 5% to it, and that's going to be the definition of my setup time. Okay? Yes?
So from a design perspective, how are we controlling when the data comes in?
Just, well, think about it, right? I have a piece of logic. Can I get the overhead camera, please? Thank you. There we go. Now let me just see right here. So what you have now is the following thing. I have a latch with a clock. I have logic. And at the output of the logic, I'm going to go back into a latch. Or a register. Let's make it a register. Let's make it edge triggered for the time being. This makes it easier. So flip-flop and a flip-flop here. And they both operate in clock phi. Okay. So what's going to happen? This is kind of a little introduction to timing. If I apply this clock here, what's going to happen is my output, what was stored at the input of the flip-flops here, is going to propagate to the outputs. And with a certain C2Q delay. So I have a C2Q delay for this. Then my signal is going to propagate to my logic. So this gets me a certain propagation delay TP. Worst case. So you look at all the inputs and all the paths through it and say, okay, what's my worst case delay? So my delay so far is TC2Q plus TP. Now in theory, after that time, I know this is going to be stable. I can say, okay, this is going to be my clock period. This is going to be, at that point in time, I can just say clock the next register. We're going to be fine. But that means that I still could have a changing value here at the time when I get this edge basically applied here. That would be a setup time violation. Really what we're saying is you have to wait a little bit longer. Your period has to be TC2Q plus TP plus T setup. you have to add the setup time to the overall delay of your critical path. And that's going to be your minimum clock period. In reality, you're still going to have to add some extra buffers, buffer timing to it. So, well, I might be wrong. The process might be a little bit different. There might be noise on the supply rails. My supply might be not be 1.2 volt, but 1.15 volts. So I add some extra buffer time, and that's going to determine how fast I can clock this circuit. So setup time is something that eats directly into my timing budget. It reduces my clock speed. And that's why you have to be very aware of. If you violate this thing, you clock it too fast, your circuit might fail. Okay? And the same thing is true with hold time. But hold times come in a different thing. I'm going to talk about that in about 2 lectures from now. Let's stay away from it for the time being. Okay? All right. Can we get back to the camera? Okay, good. So that's the setup time. And as I said, it's kind of similar. I can do the same thing for the hold time perspective. You move the data closer and closer to the clock edge, and eventually it's going to fail. Actually, this is something very interesting here. You look at this chart. The hold time here means that I have my data, and now I have my clock edge, the clock going low. It says I have to keep the data a little bit valid after my clock goes down. But now I move towards the clock, and actually what I see here, when I plot this thing out, we see actually that this thing still works correctly for negative hold time. Actually, I might, while the clock is actually, I already might start removing my data while the clock isn't, even before the clock is there. That's all because of the fact that, again, it depends on how much charge I have this basically already sitting on that capacitor. It still will work. It will be slower, slows it down. But you see in this case, this is 0 hold time. You see that the 5% might be around 0, but actually only starts failing when I move the data. When I start removing the data before I actually have basically my clock event happening. And again, that's easily understood. If you look at this chart here again, you look at, so this is what you expect, right? Your data is a 1, so you expect a 0 here, right? And then just after the clock edge, I'm going to basically go from 1 to 0. My data, I'm just going to flip it to 0. So this would be a 1. If I do this too early, you will see this will not be a perfect 0 anymore, but you will see that this will start creeping up. You see, I get a little bit closer. You still catch something because your switch is not completely open yet. You still catch something of that transition. So this goes to 0. So this is trying to go to 1, but it doesn't have a lot of time to go to 1. So it's approximately 0. The more I go negative, however, the more I go forward with my data edge. Oops, no, it's forward. You see that this thing starts creeping upwards. Instead of 0, now it becomes something that's in between and goes higher and higher, and go to the next slide. Now, and suddenly it fails. It doesn't work anymore. You stored the wrong value basically at that point in time. Okay, you can imagine, right? If I move my data edge too much before my clock edge, I'm going to store the other value. I'm going to store that new value, where I want to get a 1. Actually, I'm going to sample the 0. Okay? But be aware that negative hold times are something that's a possibility. There's some latches that allow you to change the data, or remove the data already before the clock edge is completely completed. Okay? All right. Good. So that's kind of important because we're going to come back to that later. We'll be in some homework. But setup and hold times are very important definitions. When you do sequential design, you talk to any designer in a high-performance company, they're going to talk about hold violations, setup violations, and that's something they always run into. It's one of the biggest verification problems they have on chips. And you violate some of those things, sometimes you can just throw away the chip and start again. Okay, so what I'm going to show you now is just a couple of other ideas about how to build latches. So remember, we have seen the static one, and we have the dynamic one. Also remember that when we did, for instance, the pass transistor based, both the dynamic and the latch based, that you have to be very careful with clock overlap. The idea of clock overlap can basically make your latch do weird stuff. So here's a couple of latches, or registers really, that don't have a problem of clock overlap at all. They're built in such a way that even if you have clock overlap, it still works. The first one is an interesting structure. It's called C-square MOS. So the C-square MOS register or flip-flop. It is a master-slave structure, so it has two latches in a row. Two latches working in opposite phases of the clock. Okay? The first one is a transparent, this is the master stage, is transparent when the clock is low. This is a transparent for, this is a positive, clock is low, so this is a negative latch. Next one is transparent when the clock is high, this is a positive latch. Okay? So let's figure out how this thing works. These are dynamic latches, by the way, as you will see in a second. What's happening, for instance, look at the first one. Now let's look at the second one, it's easier. So always think about, it's easier to think in positive way than negative terms. Look at this structure. When the clock is high, what's happening? Well, transistor M7 is on and transistor M8 is on. Right? Because this is driven by clock, this is driven by clock bar. So both of the devices are on, are enabled. The input signal to the latch comes in here. This is the output. The other two transistors just look like an inverter, like a CMOS inverter. You have a PMOS and an NMOS driven by the same signal. So you can look at those two devices as enabling devices. When the clock is high, those two transistors are on, and we see basically an inversion. The input will propagate to the output. This is in transparent mode. Now, what's happening when I turn the clock to low? Well, I'm going to turn off M7 and M8. Right, the clock is low, M7 is an NMOS, it's going to go off. M8 is a PMOS, but it's driven by clock bar, it's going to go off as well. What I effectively do is isolate the output node. Both transistors connecting to it are going to be off. So my output node will be floating, which means it's going to be in hold mode. It's just going to keep the previous value. So this is a nice latch. With 4 transistors, I'm building a latch here. Okay? And by basically making them driven by opposite clocks, I have a master-slave structure. Very simple, 8 transistor latch register, master-slave register. Pretty cool. People don't like this structure too much anymore because of the fact it's dynamic. Purely dynamic, say, well, leakage and charge storage and all this kind of thing, and charger distribution, all this kind of stuff we have been talking about. So typically we'll also add some keepers to this. Some way to make sure that we restore the value at the output node. So make it pseudo-static, like we know how to do. Okay? Now, there's a claim. There's an interesting claim, and I definitely would like you to check it out. There's a claim that this circuit never can have a race condition, even if there's clock overlap. If there's clock overlap, you can actually demonstrate that an incoming change, a signal here, even if both clocks are high, clock and clock bar are on at the same time. That's what clock overlap does, right? Either both clocks are 0 at the same time, or both clocks are 1 at the same time. This structure has the property that an input signal never can go to the output node in one shoot, even when there's clock overlap, which is a very interesting property. This is why this latch was very popular in a logic family which is called NORA logic. NORA stands for no race. Okay? It says there's no possibility if races in this logic family, even when there is clock overlap. Okay? So you can be a little bit more wishy-washy with your clocks here. The only thing that can make it fail is when you have clocks that change very slowly. When your clocks really change very slowly from 0 to 1, you have long transition time, and this thing can go wrong. So I definitely would like to invite you, it's actually in the textbook, but just think about it a bit. Just think about why it is so that this logic family will never allow, even with overlap, for an input to go to the output. Okay? Now this is NORA, or C-square MOS. Actually, it's still annoying, right? The fact is, this still has 2 clocks. Question now is, can I, by carefully looking at this logic structure here, simplify it in such a way that I get rid of 2 of the clocks? Actually, I would like to get rid of clock bar altogether. That would be nice. Then I need only 1 clock. Life is easier, life is more beautiful, and you never have race condition because you don't have the problem with clock overlap. If If you have only one clock, clock overlap doesn't exist. So it was in the late 80s that Christer Svensson and some people over in Sweden come up with this idea. Said, they looked very carefully at this structure and said, there's too many transistors in here. Some of those transistors don't do anything. You can just get rid of it. And you can translate it into something like this. This is a no latch now. This is not a C-square MOS latch. This is 2 stages of 3 transistors. But this is a positive latch, this is a negative latch. And you can see that both structures only use clock CLK. There's no CLK bar here anymore. If you can look at this, when both clocks are high, these are 2 inverters in a row. Right? If both clocks are low, there's no path that goes from the input to the output. It's basically in halt mode. Same here, when both clocks are low, the PMOSs are on, these are 2 inverters in a row. If 2 clocks are high, or the CLK is basically high, both transistors are off, and you see that we're either going to that this signal will propagate to the output. And we basically store the value here as a dynamic latch, basically. Now you can combine those things together. Well, I can include some logic. And I create a latch like this. Remember C-square MOS? You had 8 transistors. This is a little bit more. It's 9. But it has a single clock. It's a fairly complex structure, but it's a combination of those 2 latches that I just showed you before. This is called TSPC, True Single Phase Clock. You only need a single phase clock. So people are always innovative in the way you come up with names here. But this TSPC is a very interesting logic style. You can use registers, make master slave type of things, and then never need an inverted clock. And as a result of that, you don't have races at all in this particular structure. I'll come back to this one at the beginning of the next lecture, briefly. Okay? Good. See you on Friday.